Is my voice okay? Yeah, okay, perfect. So I want to begin this presentation by thanking again the organizer of this tremendous colloque, and I'm very, very happy to this opportunity to present my work and my research. So I will talk about Leibniz's work on mathematics. So I did a PhD on combinatorics in Leibniz's work, and I will talk about a concept that Leibniz built when he was 30 years old, and this concept is named pronic, and I want to talk to put this notion in a more general speech, which try to handle the question of the bridge between discrete and continuous, and this question. To handle this question, we have to talk about the differential calculus of Leibniz. So I will put this notion in the history of differential calculus in Leibniz, but that's not the only way to build an historiographical discourse on this notion. But I find it interesting and more maybe didactic for those who are not mathematicians. Those of you who are not mathematicians. So at the end of this life, Leibniz wrote a treaty, a famous treaty, which is called Historia et Origo Calculi Differentialis. So history of an origin of the differential calculus. And in this text, Leibniz described the way he discovers the differential calculus. So it is a very, very precious text because the actor himself make an historic discourse about his own method of discovery. Yes, the retrospective aspect of this text is clear, but that is interesting anyway. So in this text, Leibniz says that there is 3 roots to his differential calculus. So the first root is the characteristic triangle. So it's a geometric root. So it's the fact that you got 2. So you see the blue curves. You get 2 triangles, a big one and a small one, and these 2 triangles are similar. So you can use the Thales theorem you learn at school to get this equation and to have a relation between the infinitesimal evolution and the global property that are the tangents. Okay, that's the first root. The second root is the transmutation method. So the transmutation method is a geometric method that Leibniz developed in Paris when he learned mathematics when he was young. So I make the the diagram, but so you see the blue curves, and the transmutation method says that the green area is the half of the red. So if you look at the sources, you got two types of transmutation method that Leibniz used. One is the first red area, and the other is the second red area. But the principle of the technique is the same. So to understand better this method, I make an animation. I hope it will work. Yes. So you see that you have the same. You can by the fact that a triangle, the area of a triangle depends on the height, you can transmute the area of the triangle linked to the curve into an area of a rectangle. So if you make it for many small triangles, you obtain that the green area is the half of the two red area. Okay, so that's the transmutation method. For this, I make an animation too. So you see, you make many triangles. You make them smaller and smaller, and then you make the transmutation method, and you obtain another curve. And this curve is the transmutate curve. And in some cases, you get new curves that you can compute on when the first curve you can't. And that's the case of the circle. That's why this method was very useful for Leibniz, because for the circle, you can't compute the area with the curves, but with the transmuted curve, you obtain the arctangent, inverse of the tangent, and then you can. So I make a lot of animation to illustrate. So you see the arctangent with the transmutation method. Okay, so that's the second route. And the third route is the finite differences. So if you get a progression, for example, the progression of cubic numbers, you can build what Leibniz called a triangle of differences. So you put each differences of each number. So here you see each number, it's the difference between two numbers below, and you make it again and again and again. And with such a diagram, numerical diagram, you obtain property of progression that are the same of property in differential calculus. For example, here, that the third difference of the cubic is 6. And that, for example, that the fourth difference of the cubic is 0. And you can obtain that the differential of a geometric progression is always, is again a geometric progression with the same reason. You can, you can obtain other property that if you sum all the terms of the differences, you obtain the difference between the two extreme terms. So here, for example, sum of 1 plus 7 plus 19 plus 37 equals 64 minus 0. So that's the fact that the whole equal to all is the sum. Big mistake of orthograph. Whole is the sum of its parts. Okay, I passed this one. So another property that you can find is that you can obtain the extremal by the second difference, not the first difference. That's a property that Leibniz discovered very early, in a very early period in Paris. So here, for example, if you sum 6, 12, and 18, but you have to multiply each term by the natural numbers. So 1 multiplied by 6, 2 multiplied by 12, 3 multiplied by 18, you obtain the difference. And you can also, yes, so you can obtain that. So if you look the parts and the difference between the parts, you obtain this result. And that's the way Leibniz discovered it. So you have 3 times the first, 2 times the second, and 1 time the third. Okay, and this property can you can transfer this property to the differences. So, for example, here you want to find a progression such that the differences of that progression is the progression given, and you can use this property to compute the sum. So if you look at the sum of differences equal to the sum of differences equal to the differences of the higher progression, and the differences of the higher progression is the sum of the given progression. So you can obtain the sum of the given progression by the differences of this progression. And that's the same fact that the transmutation method, in which you can obtain the hierarchy by the tangent. That's the same reasoning. So it's the three roots. These 3 roots are very useful and important for Leibniz. So yeah, that's a discrete model of what we call now parts in integration par partie. I don't know the English word. Integration by parts. I don't know the English word. Okay, another. So yes, that's the roots, and in each root you can so another property which is important that Leibniz find in such triangle of differences, it is the symmetry of the diagram. So for example, here you have a diagram for geometric progression. You multiply by 3 on each line to one term to the next. And in diagonals, you multiply by 2. And so you can inverse the triangle and obtain another triangle with other property. So you find it in a very early draft of Leibniz, which is from the first year of his Parisian stay. And Leibniz say, in the same way, the primitive differences are the term of a progression whose reason is the data minus 1 unit. So in the diagonal, you get the geometrical progression with a reason with one unit minus than the given, and this is why in this case the terms are decreasing. Hence, the admirable result of decreasing fraction progression, namely that the given fraction progression and its difference with the units are generative of each other. So you can generate terms. So the progression can generate the triangle, but the terms of the diagonal can generate the triangle too. The generation is in the two ways. Okay, so there is a bridge between discrete and continuous that we can see in such roots, and this bridge, so for characteristic triangle, it's to put the triangle into a point. Okay, so lot of animation. In the transmutation method, so you have to reduce the triangle to get the curves. Here, okay, you see. And in the finite differences, it's the same. You have to find the more and more close value of the progression to get into the function. So that is what we learned at school with quadrature. The same reasoning. So in all this view, we can deduce that the bridge between discrete and continuous, this bridge is based on the notion of approximation. But I want to show you that it is far more complex than that, and that bridge was not so easy to build for Leibniz and for many of his contemporaries. So I will quote a first. I will quote a letter from Leibniz to the Royal Society of the first year in Paris. And Leibniz said that with the triangle of differences, you can generate the progression with the diagonal terms. And he called these diagonal terms generative terms, and to generate the term of the progression with the generative terms, you have to use the combinatorial number. So you see here at the end of the quotation. So for example, 27 equal 0 multiplied by 1, 1 multiplied by 3, 6 multiplied by 3, 6 multiplied by 1. So 0, 1, 6, 6 are the generative terms, and 1, 3, 3, 1 are the combinatorial number of the triangle of Pascal. So the triangle of Pascal is a fundamental figure of the triangle of differences. So that's a diagram Leibniz put in his text Historia et Origo Calculi Differentialis. And you see that you can see the triangle of Pascal as a triangle of differences. So here, it's a triangle of differences. If you see, the terms are the difference between two terms before. Okay. And there is another issue that is, for example, the triangular numbers that here, the 1, 3, 6, 10, 15, you can express it by two expressions. You can express it by the expression well known of triangular number, that is the half of the product of two neighbor numbers. And you can express it as the first figure-eight number, not the first, the second figure-eight number of each type of figure-eight number. So for example, 1, 3, 3 multiplied by 4, 3 multiplied by 4 multiplied by 5, 3 multiplied by 4 multiplied by 5 multiplied by 6, divided into and so forth and so on. Okay. And Leibniz say that the inverse of the combinatorial number represents a triangle of differences too. You have to multiply each line by a given coefficient, but if you multiply, you obtain another triangle, which is a triangle of differences. So in Leibniz, this other triangle Leibniz called the Leibniz triangle is his own triangle, and it is a complementary for him to the triangle of Pascal. Okay, so you have a structure of two triangle of differences based on this progression of combinatorial numbers. Okay. I don't know. Okay. This progression, another contemporary of Leibniz wanted to solve the problem of this progression. So the problem of this progression is to find the curve which correspond to this progression, as you say that the hyperbola correspond to the square progression. So can you find a curve that correspond to combinatorics progression? That's the problem Leibniz encountered, and he encountered it after another of its contemporary, who is Wallis. Wallis encountered this problem in his book Arithmetica Infinitorum, and in this book, Wallis wanted to find numbers between the terms of the arithmetical triangle, and he find people who read Wallis thought that he succeeded, but if you read Wallis in his preface, he tells that he didn't succeed, because what he wanted is to find a rational way to express it, and he had the intuition that it was not possible. So I read it. I read it because it's important. But where we next proceeded to other series, which were as the square roots, cube roots, etc., of those augmented or diminished series, which have a direct and immediate bearing on quadrature of the circle, ellipse, hyperbola, on which alone we made a difficulty. I saw that I was there brought to a standstill, and that I was not able to extricate myself as easily as before. Having tried the thing in various ways, there was nevertheless no way out of it that would satisfy all that was wished for. From that, it came about, I believe, that the ratio that was sought to be of a kind that was not to be expressed in true number, nor indeed in third number, as they are commonly called. For I had found some progression of numbers, so that's the progression I want to talk about, between given terms of which another term was to be interposed in order to express a sought ratio. Moreover, those progressions are of such a kind that they cannot be said to be either arithmetic, with the continual increase are equal, or geometric, where the continual multipliers are equal, but are such that the continual multipliers include arithmetic proportionals and are therefore yet more complex than geometric progression. Moreover, although in a geometric progression where the continual multipliers are equal, it's sometimes the case, for example, 1, 4, 64, that the means that have to be interpolated between the term of it are expressible numbers. The same is not possible in every case. So, thus in 1, 2, 4, 8. But it may be necessary to indicate an impossible number in some way, for example, a square root of 2, square root of 8. I judge that I will be much less to be hoped for in a progression yet more complex, where the continual multipliers are continually increasing or decreasing, that this might always be done. And therefore, I thought that there must be introduced some other method of notation than any so far accepted, by which such an impossible number might be indicated. Okay, so this problem was a really difficult problem, and Leibniz read Wallis very early in his mathematical career. So in the middle of his Parisian, during all his Parisian stay in many stages, and so there are already okay, and okay, so in a text of Parisian period, Leibniz say that there are already very difficult problems which consist in finding the mean of the progression, that is to say, given an interval to intercept the applicated of this curve between two ordinates. So the problem is explicitly given to know if there is a curve which corresponds to a progression or a progression which corresponds to a curve, which is a fact that is very fundamental in the book of Wallis, which based his computation method on arithmetic to transfer it to geometric curve. That's the mean of the book, Arithmetical Infinitorum. Okay, so you find such diagram in Parisian period of Leibniz, which he tried to find value between the triangle, the arithmetical triangle, but let us further. So he say the text beside this diagram. Let us further imagine that by continuously intercaling this mean in this way, we describe combinatorial lines by which we would represent the progression of the figured numbers. And we must see, on the other hand, if by cutting this line into unequal parts, we can express reciprocally the powers which correspond to the binomials. It is as much necessary to extract from the arithmetic triangles that one must cut into unequal parts, etc. So that, in addition, we can demonstrate this universally by dividing any power into an infinity of small ratio and showing that they coincide with these combinatorial lines. So the hope Leibniz hope with these combinatorial lines to find a way to generalize the binomial formula too. Okay, another attempt a little later is this one. So Leibniz tried to put the value of the combinatorial number into ordinates, and he finds that there is a problem because you will find you will find different value, different ordinates for same abscissa. So it can be seen from this method that you cannot lead a curve because it must have the same ordinates. For example, it is equal to the quantity 2 and the quantity 6 at the same time. So in this attempt, it seems that Leibniz has the intuition, like Wallis, that it is impossible to find such curves. So the pronical notion will answer this question in two ways. So I will present very fast these two ways because there is no more time. Okay, so I passed it. So I introduced the pronic notion. So the pronic notion is a progression of, so it's a progression Wallis talked about. It's a progression of term, multiplied terms of an arithmetic progression. So you get A, and the second term is A multiplied by A plus B. The third term is A multiplied by A plus B multiplied by A plus 2B, and so forth and so on. So this is a pronical progression, pronic progression. Okay. And in a text, in the draft where Leibniz introduced this pronic progression, Leibniz used a new notation, it is an exponent in parentheses. And so he wrote that the third power, the fifth power of y here, for example, is the first terms of the pronical progression. This being the case, so Leibniz wrote, this being the case, for the sum of such series, we must apply the general method of my differential calculus and transfer it in all generality from the lines to the numbers, as this approach allows. Let dy be the difference between this y, and p means the exponent of the degree, which we find it convenient to call, after the manner of certain ancient arithmeticians, the pronic power. And in this draft, Leibniz show that with this notation, you can find the same property as the property he knows in differential calculus for curves. That is that the integral of the p of y exponent p is y exponent p plus 1 over p plus 1. And he said, therefore, in general, you have this, this formula in numbers. So this property is valid in discrete realm and in continuous realm. And Leibniz built a new notion. So the notion of pronic is built in a way that we can find the formula, the same formula. So the principle is the analogy based on the form of the form than this symbolic form express relations that are valid in the two realms, but with different notions. And that's the first solution pronic can give to this problem. And the second solution is to find a curve, because Leibniz wanted to find a curve which is a pronical curve. And there is another draft Leibniz wrote on this problem. And this draft, Leibniz developed a notion which we can call now a continuous product. So that's the same, that's a product of an infinite number of terms in the same way that integrals are the sum of infinite number of terms. Okay, so there is two texts in which Leibniz talk about such notion. The first text is in Paris. It's an earlier text, and Leibniz talk about small ratio, so infinitesimal ratio. So he talk about the logarithmic curve, and he wants to say that in the logarithmic curve, the ratio between two extremal terms is the product of the infinite small ratio of each terms between the two extremal terms. So the ratio of two neighboring projected to each other is indeed infinitesimally small, and yet it can be called, in a way, small ratio. The small ratio is always the same, and that is why the ratio between the maximum and the minimum projected is equal to the product between them of the infinitely small ratio that is multiplied as many times as the number of points by which the height is divided. So that's the idea. Even if geometrically proportional projected differ only from infinitesimally small straight segments, these infinitesimally small straight segments are no less quantity, although their relation to sensible is infinite. So he talked about the fact, like David mentioned on Tuesday. That is all what I presented doesn't touch the question of the actual infinite or the ontological status of the infinitesimal. Leibniz is well aware that you can find a way to Archimedean method to make a bridge between discrete and continuous, but this bridge is made by approximation, and that's the object of my presentation. So if it's a bit a reconstruction, but if you see, so the ratio of the two extremes equal to the product of the infinity small ratio. If you say that like the logarithmic curve, the function is the solution of a differential equation, like here, you can rewrite this equation with this equation, and you obtain this one. You obtain this one, and this one is a definition of an integral product which was introduced by Volterra in the 20th century. Okay, so that's the first way Leibniz worked on a continuous product, and the second way, is in the draft on pronic curves. So moreover, from such a general method, we must arrive at the specific method of pronics, where we must consider that the logarithm of the ordinates are the sum of the logarithm of the number of the arithmetic progression. So he will use the logarithm to transform products in sum. So here, if you have a product, the logarithm transform it into a sum, but the problem that Leibniz didn't see is that you must multiply the terms of your series by the infinitesimal dx. So here you must multiply by an infinitesimal e in order that the series is doesn't diverge. So Leibniz didn't do that, but he built a curve that corresponds to the right notion. So the idea was there. So if you have so this formula, the product of each term to the power of ds. If you take the logarithm, you obtain an integral. And so if you apply the inverse of the logarithm, you obtain the continuous product. And Leibniz wrote a diagram which corresponds to this construction. Here you got the logarithm. So the blue line is the logarithmic curve. The curves below is the integral of the logarithmic curves, and the curves on the right is the chronicle curve searched by Leibniz, which correspond to this notion of continuous product, but you lose the interpolation property, because if you interpolate the continuous product, you don't obtain a chronicle progression. So that's the other way Leibniz wants to solve it, but it has also a issue. Okay, so I will conclude that the fact that we see approximation in the bridge between discrete and continuous is a category of actors, because actors told that, but it's also a category of historian, because we have now many tools that can interpret all those problematic in such a relation between discrete and continuous, and tools that were not disponible in the 17th century. And so the problem of this bridge was that it exists some progression which are in some way purely discrete, in an incompressible way discrete, and this progression was an opportunity for Leibniz to develop many new notation, new notion. And for the end, I think that the tabular structure of diagrams is really important in this problem, because when you make the approximation, you break the symmetry of the diagram, because the order of derivation remain discrete, and the symmetry of the diagram, the symmetry of the triangle of Pascal and the symmetry of the harmonical triangle are essential property to make the construction that Wallis made, Leibniz made, and another author I don't talk about, it's Mengoli, which made the same research. Well. Okay.